Hello everybody, welcome to yet another video. Today we'll be talking about organic reactions. So there are many types of organic reactions, but firstly we'll start by defining what organic reactions are. So organic reactions are typically chemical reactions that involve organic compounds, as easy as that. So there can be many types. We can have rearrangement reactions, elimination reactions, substitution reactions, addition reactions, reduction reactions, oxidation reactions. All these are examples of organic reactions. But for the sake of this video, we'll only stick to the four types: rearrangement, elimination, substitution, and addition reactions. So what does it mean when you say a rearrangement reaction? A rearrangement reaction means exactly what you think it means: to get a particular substrate from one particular order and change it into another particular order without eliminating or substituting any of the functional groups on that particular substrate. So there are many types of rearrangement reactions. We can have the Favorsky rearrangement, the Pinnacle rearrangement, but for the sake of this course, we'll focus on two main types of rearrangement reactions that you typically see in an organic chemistry course. The first type are the ones we call hydride shifts, and then we'll also have alkyl shifts. The most common type of alkyl shift is the one we call a methanide shift. So what does it mean when you say a hydride shift or an alkyl shift? Let me give you an example. Suppose you had a molecule that looked like this. When you look at this molecule, what you'll be able to see is you have a cyclohexane attached to this portion here that's connected to a bromine. First thing you need to know, if this was in an environment where water was there, right? One thing you'd be able to see is that this bromine is a very good leaving group. Because it's a very good leaving group, it can do, well, it can leave, right? So when the bromine leaves, one consequence of the bromine leaving is that it creates a carbocation where it left. So meaning this position will have a carbocation. One thing you need to know about carbocations is carbocations are not stable when they are on low degree carbons. What am I trying to say? Carbons can be classified in different ways depending on their degrees. So if a carbon is attached to one other carbon, we say it's primary. When a carbon is attached to two other carbons, we say it's secondary. When a carbon is attached to three other carbons, we say it is tertiary, right? So one thing you need to know is that when a carbocation forms on a low degree carbon, it's not stable. And so the carbocation must move. There must be a rearrangement in the molecule such that the carbocation moves to a higher degree carbon. So when you analyze this molecule, you'll be able to see that where the carbocation is, that's an example of a second degree carbon. Let's look at the molecule. When you look at the position towards the left, you'll be able to see that we can locate we can locate a tertiary carbon, and therefore the carbocation must move from this position to this position. How is that possible? The movement of the carbocation is only possible if a hydrogen shifts from this position to that position. We call that a hydride shift. A similar thing can happen with a methyl group, and then we call that a methanide shift. Suppose you had a molecule that looked like this. Same analogy, when the chlorine leaves, the chlorine is a good leaving group, it leaves a carbocation behind, and then the carbocation is not stable on a secondary carbon. We look at the molecule and then we're able to spot a quaternary. We're able to spot a quaternary carbon, and therefore the carbocation must move from this position to a higher degree carbon. And then in order for it to move, there must be a shift. So the only thing, since this carbon does not have any hydrogens, a hydride shift is impossible. Therefore, we'll have a methanide shift. The entire methyl group will shift from this position to that position. Those are rearrangement reactions. The next type of reactions are the ones we call elimination reactions. To eliminate means exactly what you think it means. So to eliminate means you had something in the molecule and you remove and have two products. Generally, you'll be able to see that elimination reactions lead to higher entropy. We'll talk about that in another video. So there are two types of elimination reactions. You can have concerted reactions. An example is elimination 2 reactions. What concerted means it means happening in one step, and then non-concerted reactions, meaning happening in two steps. An example would be E1 reactions. We'll talk about these in more detail. So generally, how will these reactions look like? Suppose you had a reaction that looked like this. First thing you'll be able to see, in an elimination reaction, we use a base. In a substitution reaction, we use a nucleophile. That's the first difference you need to take note of. So what happens? The base, we defined a Lewis base as the ability to do what? Ability to donate an electron pair, right? So the base donates an electron pair, thereby extracting a hydrogen from the compound. When that happens, the hydrogens or the electrons that were used to form the bond will move towards the molecule, and then they'll be used to form a double bond in between the two carbons. When this happens, it creates a problem. That means the carbon to our left is attached to 5 things, and if you can remember, carbon needs to be attached to 4 things. Therefore, the leaving group X must leave. This is an example of a concerted reaction, and then the product will look like that. The second situation would be a non-concerted type of reaction. An example would be an E1 reaction, where it happens in 2 steps. So in order for this reaction to happen, what will happen is, firstly, the leaving group has to leave. So that group X will have to leave. When it does, it leaves a carbocation behind. The second thing we need to check if a rearrangement reaction is possible. So we check for the degrees of the carbon. It so happens that all the carbons are tertiary, so meaning no rearrangement will happen. The next thing that happens is that the base does the same thing it did in the previous reaction. It donates a pair of electrons, therefore extracting a hydrogen. When that happens, the electrons that were used to form the bond with the hydrogen are used to make a double bond, thereby producing the same product. So regardless of whichever elimination reaction you use, the product you form is the same.